Lesson 6, Frequency Response. Section 6.2. Frequency Response in High Frequency Region. Subsection 6.2.1. Equivalent Circuit. This is an emitter common connection using an NPN transistor. It is rotated 90 degrees counterclockwise. Then the position of VBB is shifted without changing the circuit topology. A signal voltage source Vs and a resistor RL are inserted. This is a common emitter amplifier. And this is the equivalent circuit of a common emitter amplifier. In the frequency region higher than 100 kHz, we have to incorporate more elements of the transistor into this equivalent circuit. The impurity density in the base region is made low during fabrication. Due to this low impurity density, the base region has a small amount of resistance. This resistance is called base spreading resistance. RB represents this resistance. Vs controls the amount of electrons from the emitter region to the base region. The electrons in the base region diffuse through it, and reach the collector region in a short period of time. The speed of diffusion is not affected by Vs. Therefore, if the frequency of Vs is very high, the diffusion period acts as a delay in response to Vs. This delay can be represented by a capacitance Cπ. This capacitance is called base diffusion capacitance. The PN junction between the base and collector region is reverse biased. Across the junction, there is a layer called depletion layer where no mobile carrier exists. Outside of this layer, there are carriers. Two parallel conductor plates sandwich an insulator layer. So, this forms a capacitor. This capacitor can be expressed by C mu. This capacitance is called the collector base junction capacitance. Subsection 6.2.2. Parameter values. According to Mark Thompson's book, entitled Intuitive Analog Circuit Design, and the data sheet of 2N3904, RB is approximately 100 ohms, Cπ is approximately 45 picofarad, and C mu is about 2.6 picofarad. We use this equivalent circuit for the analysis in the high frequency region. Let's neglect HOE for its small influence on the amplifier characteristics. Subsection 6.2.3. Frequency response. Let's analyze the frequency response of this common emitter amplifier with the bias circuit, in the high frequency region. In the high frequency region, C1 and CE can be considered as short-circuited, due to their small reactances. Therefore, C1 and CE can be omitted for the frequency response analysis. The signal source V1 and Rs, as well as the bias resistors R1 and R2, can be simplified using Hoth-Thevenin's theorem, in the same manner as in section 6.1. This is the equivalent circuit of the amplifier including the bias circuit in the high frequency region, where VHT and V2 are complex numbers. RHTB denotes the composite resistance of RHT and RB. VB' denotes the voltage between B' and A. Then, IB equals VB' over HIE. Thus, HFEIB is changed to GMVB', where GM is called the transconductance. ZE denotes the composite impedance of HIE and Cπ. Using the loop current method, we obtain these three equations. Then these three equations are reformulated to this matrix equation. V2 is given by this equation. ZE is the composite impedance of HIE and CPi, and it is expressed by this equation. By solving the matrix equation with respect to I1 and I2, and substituting them into equation 6.9, we obtain this equation. This equation is quite complicated. Fortunately, these two terms can be neglected because they are negligibly small, in the frequency region lower than 1 MHz. For example, at f equals 500 kHz, they are 0.00049 and 0.011 respectively. On the other hand, these two terms are 0.21 and 1.7. These two terms can also be neglected, because they are far smaller than GMRL. Then, we have this simplified equation. This term is denoted by C. Miller, and is called Miller capacitance, named after John M. Miller, who discovered this effect. The collector base junction capacitance Cmu is small. But, in the input circuit, Cmu acts as a very large capacitance. This is represented by the equivalent circuit using the capacitance C. Miller. C. Miller is 1 plus GMRL times larger than Cmu, and its value is 150 picofarads. This effect is known as the Miller effect. The Miller effect is intuitively explained by the voltage Vcmu and the current Icmu. Vcmu equals Vb prime minus V2. V2 equals negative GMRL Vb prime. Thus, Vcmu becomes 1 plus GMRL times Vb prime. This means that Icmu is amplified to 1 plus GMRL times larger than the case, where only Vb prime is applied to Cmu. From the viewpoint of Vb prime, the capacitance Cmu appears 1 plus GMRL times larger, and it is C. Miller. Exercise 6.2. This is your homework. Pause the video, and answer the problem. This equation can be modified using the definition of Gm in equation 6.6. This equation has one important frequency. F3 denotes this frequency, and it satisfies this equation. Then, F3 is obtained as this equation. In the region where F is much lower than F3, this term can be neglected. Substituting VHT with equation 6.4, the relationship between V2 and V1 is obtained. Then, the voltage gain AV and the phase difference psi V2 to V1 are derived. This is the same as in equation 6.3, except for RHTB. If we incorporate the base spreading resistance RB in the analysis of the low frequency region, equation 6.3 becomes identical. Thus, this equation is valid in the region where F is much higher than F2 and much lower than F3. If F is much higher than F3, then this term becomes negligible. AV and psi V2 to V1 are given by these equations. In the high frequency region, AV is inversely proportional to the frequency. These are line graphs based on the derived approximations of AV and psi V2 to V1. The results of experiment 6.1 are superimposed. The approximate lines in the low frequency region are combined with those in the high frequency region. F2 and F3 are cut-off frequencies. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.